Start recording, and we're live. We're recording. Hi, John.
Hi, Mikey.
How are you today?
Not doing too badly. How about yourself?
Yeah, I'm okay. Quite excited about this first recording. A bit nervous, I guess, but we'll just see how it goes.
I'm sure it'll go well.
So the topic today is, well, a lot of this series will have to do with reformulation of the whole of math. So do you want to take it from here and make a brief introduction about your work in the field and tell us about it?
Sure. Well, it's not really strictly a reformulation, but a revision rather, because not all of math is formulated incorrectly, but there are numerous parts of it which are. And the fundamental concepts, such as number and arithmetic mean, etc., need to be well defined, because that helps students and aspiring mathematicians to want to learn more mathematics and to proceed from a foundation of understanding rather than learning things rote and applying the results of such theory.
Right. Okay, so just to compare and contrast, first of all, to let everybody know, you do know the, quote, mainstream approach to mathematics. You do have a mathematics degree. You understand set theory and the whole constructivist method and the history of how it all came about. And we can compare, contrast the two. So in your theory, or the correct theory in a Platonic sense, the absolute theory, is number the most foundational aspect of mathematics? Where do we begin from? Or should we firstly define number? And then I made a small introduction about the mainstream theory because I have a book here from Terence Tao, supposedly the greatest mathematician, whatever. And it's the typical mainstream theory. And I was reading the first pages and I saw that actually number is never defined. It's just sort of with a sleight of hand defined as a set, but then a set is defined in terms of, and it starts to become circular. So sorry for blabbing on, but let's begin. So what is number?
Okay, I'll tell you what number is, and I'll give you a definition for it. But so you say, where do we begin? Well, and why is number the most important concept? Because number allows us to perform quantitative measurement. But in order to get to a point where we actually understand what quantitative measurement is about, we have to go back to the beginning where we formulate the concept of number. Okay?
Mm-hmm.
So that begins with Euclid's Elements, where Euclid starts off with using magnitudes that are that take the form of distances, okay, lengths or distances. And of course, his approach is qualitative. His measuring approach is qualitative. He doesn't have number, not until book 7, in fact. So what you have is the 5 requirements, which are vitally important and can be derived systematically from nothing. They are not axioms as erroneously thought by mainstream academics. They are actually systematically derivable from nothing. And so those 5 requirements are what we use to build up the theory so that we can begin to talk about quantitative measure. Because till book 7, we do not have quantitative measure. It's all qualitative or geometric. Okay, so book 5 is where the cogs and wheels of arithmetic and number are laid or are established in a very firm and rigorous way. without using number as such. Only magnitudes and ratios are used. And then, of course, the transition from magnitudes and ratios to number is done via the abstract unit in algebra. So the abstract unit doesn't concern itself with size any longer. But in geometry, you're always dealing with a unit which has a size. It has an actual size, but you don't know what that size is. You can't measure it in any other way but in terms of a ratio, and what you have are proportions between magnitudes. So there's no single way in geometry. There's no single way in geometry to talk about 1, 2, 3 as you do in algebra. So algebra is basically the ability to talk about those measurements with unique numbers, right? In other words, knowing exactly what they mean. So just a very quick example. In geometry, if you have two proportions, a half and 2/4, they may not necessarily be equal. In fact, unless you're using the same unit, they won't be equal, okay? Because the antecedents of the half and 2/4 are different lengths. But if you look at it in terms of proportion, 1:2 as 2:4, right?
Yeah.
So they are in proportion, but they're not necessarily equal. In algebra, that changes. We don't care about the size of the unit anymore. We just transfer all the properties of geometry and we say a half is equal to 2/4.
Right.
Does that make sense?
Yes, it does make sense, and details about that can be found on a lot of your videos where you specify the difference. So back to the difference, requirements versus axioms. Requirements in ancient Greeks is aitήματα, and you hold very correctly, might I say, that aitήματα are very different than the modern concept of axiom. So I want to take. I would like you, please, to analyze this from two different perspectives: from bottom up and from top down. From bottom up, does the issue start with the wrong translation of the elements that has come down to us from the English authors? That only the translation happened 100 years ago, and they had no maybe good understanding about the background or what Euclid was trying to do. And they implemented their own understanding of what aitήματα means, or what arithmos means, what number meant. And then from the top down, the whole axiomatics was a whole system. It was a project that they tried to correct mathematics in their own view. But so would you like to start from the translation and why was the word aitήματα converted into axiom? Where did that begin?
Because I think when Thomas Heath and others that were translating the elements, the mainstream mathematics community had already begun work on new foundations of mathematics, which were set theory. And so they didn't really understand how Euclid got the first 5 requirements, and there's a good reason for that. Euclid didn't explain how he got the first 5 requirements. Euclid should have written what I call a prologue to the elements, right? And the prologue explains how these 5 requirements are systematically derived from nothing. In other words, we begin with a straight line, then a straight line that can be extended or shortened, then the circle, then everything else comes out of the circle, the right angles, the parallel lines, all the other geometric objects, in fact, come from the previous requirements, the circle and the straight line, and the extended or diminished straight line. And the circle itself depends on both the first 2 requirements. You cannot define the circle correctly without using the previous 2 requirements. Now, I don't know if Euclid was aware that these things could be derived systematically. And to my knowledge, there is nothing that we know from the ancient Greeks about anybody who wrote a prologue to the elements. It was basically understood that the 5 requirements were true. And I'm sure that before they got to that stage, they were already aware that that could be done. In other words, they could be derived systematically. So Euclid didn't spend any time on it. What Euclid was trying to do was put together the world's first textbook, not on mathematics, but on how to think systematically and properly, because everything that is done in the elements is really a template for well-defined thought. It's not per se a book on geometry or mathematics or how to do constructions, but a theory of how one can think correctly and prove things systematically. And even there, I'd say that Euclid did go overboard in some cases with the proofs, because they could be done a lot simpler using constructions, or not constructions, but actual geometry itself. And so there was a lot of confusion about that. There's always been confusion about the elements. I don't believe anybody really understood what Euclid was attempting to do, which very importantly was move to a stage where quantitative measure could be performed. Okay, and now there's nothing more important than quantitative measure, because without it, you don't have any other science. How can you do physics? How can you do chemistry? How can you do engineering? How can you do computer science without numbers? You simply can't. Okay, so what happened was that they took the parts that they understood, like the theorems and the propositions, and they used that, believing that what those theorems and propositions were constructed on was true. They didn't derive it systematically from nothing for themselves, which is what they should have done. And in fact, they did quite the opposite. Because they were so inept and so incompetent and could not do it, they decided that, well, it can't be done. Therefore, we just need to believe in it because we know that the results are true. But that was not the case. And as I've shown in my publication called "There Are No Axioms or Postulates in Mathematics," it's not the case that the 5 requirements are axioms. There's no mention of the word axiom or postulate or any such thing in the 5 requirements. And there are Greek mainstream academics who agree with me on this point. So I'm not alone in saying that the 5 requirements are not axioms.
Right. So, let me see my notes here. Well, it's a bit apparent to me that somehow we got, let's say, lost in translation, because first of all, we need context to understand Euclid. A thing that provides context is that we know that we have lost 95% of all ancient Greek works. It's estimated that what was saved was only 5%. So probably there might have been some sort of prologue or verbal understanding giving context and what we got. And we can see this from Greek versions that give of Euclid's elements, that they give a lot of information about how what was the Heath, the version that Heath got. He got a watered down version of something, which that watered down version was a watered down version of something else. So one thing that I think everybody needs to understand is that a lot of things were lost. So just getting some sort of 10 times watered down version of a translation of something, and then really understanding that Euclid stated axioms in the modern notion of axioms, it's actually projecting someone's own understanding to what Euclid did. But I think what we have to do is deduce contexts from the mathematics of the time and understand what Euclid was trying to do with a more holistic view.
Yeah, I tend to very much agree with you that the ancient Greeks knew about the prologue. And of course, the Elements are not the only books that they had written, and it's quite possible that these things, with respect to the requirements, were already commonly understood by everyone. So Euclid didn't feel the need to go over those requirements again. But something tells me also that Euclid may not have known exactly how either, because certain of his proofs and propositions that come later would have been part of such a prologue. For example, parallel lines and right angles are all equal, and all those particular concepts that he used. So I'm not terribly sure, but I've outlined these things again in my article on axioms, and that there are no axioms or postulates, and I've shown that the 5 requirements can be systematically derived from nothing, and that's where we should start before we start studying the elements of Euclid or any other approach that involves an establishment of theory as Euclid was attempting to do.
Okay, so back to number. Can we state the definition of number again?
Yes, so it can be defined very simply in one line. And when I first thought about this, I used to say a number is the measure of a magnitude. And although that's very short, it's grammatically speaking not complete. So I changed that to a number is a name given to a measure that describes a magnitude or size. So a number is simply a name that is given to a measure that describes a magnitude or size. Now, that magnitude or size can be anything. It can be distance, it can be mass, it can be volume. The ancient Greeks used the most simple one that they could, which was distance, simply because they took the time to write the elements and explain qualitative and quantitative measure in terms of distance. So the magnitude that they stuck with, or they used in their theory, was distance. And think about it. It would have been pretty ridiculous if they tried to write the elements from the point of view of considering distance to be, for example, mass or volume, because all those things rely on distance being established first.
Yes.
Right?
Yes.
So they took the most common idea of magnitude, which is distance, by the way, and they built that up, and they put the 5 requirements in place, and they said, okay, so this is how we're going to arrive at qualitative and quantitative measure using line segments.
Yes, and it is sort of the most primitive concept, because this is a sort of we are spatial beings, this is a 3D world, so it's sort of it's irreducible, isn't it? It's the core. You can't reduce it any further, because you can define everything starting from that first principle, but you can't do the opposite, starting from more complicated principles and having those as you need distance to define
Correct.
Everything else, so you can't do it the other way around.
You can't. I mean, in my honest opinion, I cannot imagine anybody trying to, for example, set theory, which is such a laughable theory, and circular in so many ways. You can't say, all right, let an empty set represent 0, and then let 1 be another set with an squiggly little empty set in the middle, because that already assumes you have a notion of counting. And to have a notion of counting, you already know what is number, and you've already gone through that entire machinery that Euclid goes through to build up towards that concept. I mean, he writes 6 books before he gets to 1, 2, 3, 4, and quantitative measure. Okay, so he's got nothing about quantitative measure in the first 6 books. It's just a prelude to, or a foundation that builds up to the point where he can establish number. And he doesn't even do a very good job of it in the first definition. He says a unit is that by virtue of which everything is known as one. But I can't really judge him too harshly on that, because really what he should have just said, a unit is the abstract standard that is used for measure. In other words, the abstract unit is what we will be using to define number, is how he should have stated the first definition in book 7. In book 7, the abstract unit is the foundation object for quantitative measure. And so the generalization of all these proportions, all the proportions in geometry into algebra would happen through the abstract unit.
Yes, and maybe there were also probably sort of religious and philosophical elements around this concept of the monad, or the whole, or all is one, that maybe sort of corrupted their notion and tried to sort of base it around the concept of there has to be a monad. But in many sense, again, there has to be some sort of monad, because if we try to consider all that is, there has to be some sort of oneness to everything,
yes.
Right? Because if there wasn't oneness, then we arrive at some sort of contradiction.
Well, so, you can't have. I'm sorry, you can't have quantitative measure without a unit.
Yeah.
And so all they did with the abstract unit is they said, okay, we're not going to worry anymore about what the actual size of the unit is, but we're going to transfer all the properties across from geometry.
Mm-hmm.
You see, so we'll transfer the properties of measure that we already established in the first 6 books to algebra, so that we can do quantitative measure. Otherwise, what would you mean if you said one without some kind of qualification to it in algebra? One what?
Yes.
You're talking here about one abstract unit or 2 abstract units, and it's a quantitative measure. When you calculate the area under a curve in calculus, what are you doing there? You're using abstract measures, aren't you? Because you're not, when you say it's so many square units, that's all you do in mathematics. You don't say square meters or square miles. You just say, oh, the area is x square units, yes, because you're using the abstract unit. In physics, you go a step further. You take the abstract unit and you add an actual physical unit so that we know what we're talking about, right? So yes, if you say 3 meters, then we know, yes, the standard meter is so long and it's 3 of those, right? But in mathematics, we don't care about the physical unit. It's the mathematical abstract number is dimensionless. It doesn't have a dimension. Mm-hmm. The size of the unit in mathematics is irrelevant. It's mm-hmm. the abstract unit we're talking about. In physics, it's different. You have to add a qualification to the actual number that you obtain from mathematics.
Mm-hmm. Right. So, okay, back to to your definition. You use the word measure. So
I use the word measure. Yes.
Yeah, so, what is to measure something? And from your work, I understand how important it is to realize that every number is also, it can be in terms of I don't know if this is the right word, fraction, or every number is ritos, so 2 is also 2 as 2 is to 1, and that can happen for any number. So why is it so important to define and understand the concept of ratio?
Because of this, simply. So in Greek, in the Greek language, when you say ritos, it means something that can be called or named, right? Mm-hmm. And so that's what you do when you transfer from geometry to algebra. You want to name those proportions. So if you take any innumerable number of proportions of a half, you want to be able to name them in a very unique way in algebra as 1 over 2, right? 1 over 2. That is a rito. That is a ratio. So you cannot even begin to talk about number unless you're talking about a ratio, because the ratios which come from the antecedent and the consequent parts of the first ratio, are what describe the very number that you're talking about. Okay?
Yes, of course.
So, for example, a half is the description of what is a quantitative measure, because you're saying, okay, and I wish I had a screen to display this for you now, but if you take just, let's say, the length of this finger as the antecedent and then twice the length of this finger on this side, then that's one representation in geometry. But you can have many such representations in geometry.
Yes.
Okay? In algebra, you don't care about all those proportions. You just care about, they're all equal in algebra. So a half is equal to 2/4, is equal to 4/8, is equal to 10/20. There's no difference in algebra. It's the same quantitative measure.
Yes, because it's an
In other words,
abstraction.
it's an abstraction. It says the relationship between the numerator and the denominator is what gives the measure a name. Okay, the relationship between the numerator and the denominator. And so really a number in algebra is really a ratio of two ratios. What are those two ratios? The top ratio is the numerator, which is a multiple of the unit, and the bottom one is also a multiple of the unit, and tells us how many equal parts the unit is divided into, right? So 1/2, the 2 tells us that we're dealing with a unit that has been divided equally into two parts. And the top one, which is called the numerator, or in Greek, o arithmetis, which is the counter, tells us how many of those equal parts we are talking about. In other words, what measure are we talking about here? We're talking about one of those two equal parts, right? And if we said two of them, that's the same as talking about the whole part. 2/2 is 1, right?
Yes.
So go ahead.
Okay, so starting from the if we see a typical history of mathematics book, it will at some point start to talk about the Pythagoreans that believed all is number, and they assert, for instance, Boyer's History of Mathematics, but this happens in most texts that I've seen, they assert, without actually any proof, that somehow square root was this huge problem in ancient Greek mathematics. And it's totally ironic to me, because how I understand it and deduce what square root 2 is, not only was it not a problem, square root 2 perfectly illustrates the whole of their theory of how they understood what is number and how they understood incommensurability, and this beautiful relationship between things we can number and things that do not have a that we can't. But that isn't a problem, and we haven't in modern times corrected this problem because it's all circular. So what is square root of 2? Is it a number? And why in the mainstream theory have they sort of, the whole of the system is made to correct or to somehow deal with this issue of pi and square root 2 and these supposed numbers?
They're all constants. Those are all constants rather than numbers. And why do I call them a constant? Because if we try to measure them, we always arrive at the same measure, but it's never a complete measure, right? So square root 2, think about it. If you try to measure the diagonal of a square with one of its sides, you won't be able to do it. And that's a very simple proof that you can illustrate, that anybody can, that a high school student can illustrate. They say, well, let it equal to a over b, and then show through a very simple argument that it reduces to a contradiction or an absurdity. In other words, square root 2 cannot be represented as a over b, therefore it's not a number. It's a magnitude that cannot be measured. So for example, and in any case, if you're talking about different square sizes, you're measuring different diagonals, right?
Yes, of course.
So you can tell that it doesn't matter which square you use, what you're doing is you're approximating the measure of the diagonal using one of its sides. It's not even a magnitude in reality. It doesn't even exist as a magnitude. It only exists as an approximate measure, just like pi. If you take different size circles, you're measuring the circumference, right? That's what you're measuring. So those circumferences are not equal. A small circle has a much smaller circumference than a bigger circle, yet when you try to measure it with the diameter, which is a different unit, you get the same constant. So it's an abstract measure. Pi, square root 2, and any other so-called irrational number, there's no such thing as an irrational number. It's an incommensurable magnitude. And incidentally, in the Elements, they do cover this theory very thoroughly. Book 10 covers incommensurable magnitudes. So it's not like the Greeks didn't know about these things or it confuddled them. That's absolute nonsense. They were perfectly aware of it, and mainstream mathematicians of today haven't advanced even one iota over the knowledge of the ancient Greeks. Their Dedekind cuts and their Cauchy sequences are invalid constructions of that mythical object known as a real number.
Yes, you've shown this in your videos, and even Professor Wildberger,
right,
although he's very wrong about many things, let's say, he's totally in the right direction, and his criticisms on mainstream mathematics are absolutely correct, and he also has nice videos on Dedekind cuts and the issues with that. Of course, his solution in turn, I don't agree on with rational trigonometry and his whole program, and I agree with your material. But still, it's the definition of a number being irrational is self-contradictory, isn't it? Because if we understand that a number is a measure of something, and in order for something to be a measure, it has to be in some sense a ratio, because we have to compare something to something
else.
To something else, and we can use the monad or 1. So 3 is 3 over 1, and that is the definition of a number. So anything that isn't that isn't a number, and if we call it an irrational number, it's self-contradictory, and we're reifying this thing into existence out of.
And it's also redundant to call rational number, because a number is rational. So
Exactly.
It's redundant to say rational number. If it's not a number, it's not rational also, because numbers come from ratios.
Exactly, and that's what they haven't understood, because in the whole program they start in this sort of constructivist manner, this religion that they, if you try to implement set theory, and set theory is an ideology because it's sort of this notion of how to do something, and then you try to implement that, and the only way to sort of quote successfully do that is to start by constructing numbers as the natural numbers in a sort of object-oriented way that it's just 1, 2 and so on, and then sort of add complexity, and then you have the integers, and then you have the rationals. But it isn't that, because again they're defining sets in terms of themselves, because it's sets of sets of sets, and it's just sets and hypersets. So what else? Why start from geometry? What is pi? On infinity then. What is the problem with infinity?
Well, infinity is a concept that cannot be reified. And when I say reified, it cannot be demonstrated in any way whatsoever. You cannot, for example, write 3 little dots, which is called an ellipsis, after a certain series or a sequence and say that it's infinite. It's not, because that's like saying that 0.333 ... is equal to a third. That's absolute nonsense, because first of all, even hypothetically, if all those threes were there for the measure, because that's what you do in radix systems, you measure the numbers in that particular base. If they were all there, it still wouldn't be measurable in base 10, because if you've read my proof of the most important number theory, in order for any number to be measurable in base 10, base 10 must contain the prime numbers of that fraction. So 3 is not a prime number of 10. So what it's telling you is that unless that number's prime factors are 2 and or 5, it cannot be represented in 10, okay? So you need those two prime numbers, or one of them, in the number in order for it to be represented, to be measured or represented exactly in base 10. So you can represent 4 because 2 is a prime factor of 4 and also of 10. You cannot represent 3 because it's not one of the prime factors of 10, which are 2 and 5, right?
Yes.
So any number that you have must have those prime factors in the base that you're attempting to represent it with, because that was the reason for why radix systems were established, by the way. One of the main reasons was to make it easier to do arithmetic. In other words, which was a terrible thing that they did, because by so doing, people didn't have to learn about fractions and fraction arithmetic. And that's very bad, because in radix systems, especially in base 10, all you really do is approximate measure all the time, because when you write 0.333, you're saying, yes, it's an approximation for a third. It's not really a third, but it's good enough anyway. It works because it's good enough. And that's what they were wanting to accomplish. So they taught all the arithmetic operations, such as multiplication, division, etc., without having to learn any of the theory of fractions. Okay, so you could actually do things with Simon Stevin's decimal theory, which, by the way, he wrote a book on that, without understanding even really what is a fraction. So in your opinion, if you look back then, you would have said that the part that appears to the right of the radix point is less than 1. So that would be a fraction, right? And that's all they understood. They didn't even have to understand that it lies between -1 and 1 or anything like that. So they learned those methods rote. And whenever they learned the theory of fractions, they never understood it, because it was not only not taught the right way, it was taught in the wrong order. So it's okay to learn those methods that Stevin came up with, but first students should learn how to work with fractions before they do those kind of things.
Yes.
It's like to give you an analogy, it's like using a calculator. Okay, so it's great to use calculators. I'm not against them, but you first need to know what the calculator is doing, right?
Yes.
That's it.
Yes. Sorry to interrupt there, but it just came to mind how then important we understand and more foundational geometry is.
Yes.
Because it's more, we can cut any segment into 3 pieces. And we can define, for instance, the square root.
We can cut any segment into 3 pieces.
Yes, we can.
Yes.
So it's thinking geometrically and thinking of terms of construction and magnitudes is sort of more foundational than starting with this radix system and starting with this arithmetic. And we can go, and it's useful to go there as an abstraction, as a next step, but not to start with that in the beginning.
Right.
Okay. So, all these foundational issues are very important to sort of the heart of mathematics, which is also calculus and a foundation for all physics, engineering. So would you like to tell us about your work on the calculus and then compare it and contrast it to the mainstream calculus?
Yeah, it's a very huge topic, so I'll just summarize it. The new calculus is a geometric-based calculus. It doesn't use any ill-formed concepts such as infinity, infinitesimals, limits, which limit theory is itself a circular theory because in order to use limits, for example, to find the derivative, you first need to know a little trick of how to get the derivative, and it's called the first principles method. But the first principles method is essentially flawed. And what fixes that method is my historic geometric theorem. It fixes that method. So you don't even need to prove that a limit exists, because if you use that method, you'll know that that is the derivative, and that's the way that you can find it. And the beauty of it is that you can use the exact same theorem to formulate the definite integral. So you don't need things like Riemann sums and upper limits and lower limits. It gives you the exact sum of the definite integral in terms of that geometric theorem. So the definite integral is redefined rigorously, 100% rigorously. And the new calculus takes it a step further. The new calculus is also, first of all, the geometric theorem was realized from the new calculus, but the new calculus does not allow for derivatives at inflection points, because in the new calculus, a tangent is defined as a line that meets a curve at the point of tangency, but never crosses it at the point of tangency. So that's the main difference between the new calculus and the mainstream formulation. It doesn't affect the calculation of integrals or areas or volumes or anything like that, because the mean value theorem doesn't care about derivatives at points of inflection. Okay, it disregards that entirely. So it'll work whether you think about it or whether you don't. So those are the basic differences. And now a high school student can easily learn the new calculus because it doesn't involve any of those ill-formed concepts. You do not deal with infinity or infinitesimals, and you do not need to learn limit theory to do calculus. So engineers can learn it. They can learn how to calculate line integrals, differential equations, partial differential equations, which are very easy to use in the new calculus because they're well defined. They're understood. You can actually say dy dx multiplied by dx dt is equal to dy dt. Okay, those things are possible in new calculus, and they're well defined. You don't, for example, have to imagine, like Hillary and Shewhart said, that the differentials must for some time, not be numbers. It just doesn't they've really never understood their calculus. And even in the mainstream, the reason calculus works is that the results are basically correct, but the formulation is a complete disaster.
Yes, that's just a reification what they've done,
yes.
Isn't it? And
Yes.
with ill-formed concepts of infinity and so on. What strikes me is that I was looking at book reviews about what the best book for calculus is. And this book here, for instance, Tom Apostle's, is considered one of the best books ever written on the subject. And then Terence Tao's book on analysis basically states that in the introduction that analysis is a more formal and well-defined version of the calculus. It's like the logical underpinnings of it. And not only do I find loads of logical mistakes in it, not only is it didactically totally wrong, I would suggest that the best book somebody can read on calculus might be the history of calculus to really understand the concept. And I take that a step further. Students now learn things verbatim and to take things at faith. They've totally lost their intuition because, and I've seen this anecdotal evidence of how students struggle to learn mathematics and to learn these weird concepts. So Yes, maybe history. What do you think about that? About the history of mathematics being implemented much more in the education system?
It's very important. I mean, you cannot understand mathematics unless you understand the history. But before I address that topic, I just want to go back and quickly answer something you mentioned about Terence Tao. It's quite ironic that you said he considered his book on real analysis to be more formative and more formal, so to speak, because in one of his blogs, he goes on about how that proofs are not all that important, which is in total contradiction to what he said there. And anybody who thinks he's the greatest mathematician in the world is actually a clown, in my opinion, because Terence Tao is not even close to, he shouldn't even be called a mathematician because he's never accomplished anything in his life that gives him the right to call himself a mathematician. Okay, so getting a PhD or working on resolution of that green Tao theorem does not make you a mathematician. I'm very sorry, but you have to produce great works. And moreover, those great works need to be understood by the majority of aspiring mathematicians. It can't be a select group of, a select clique of small high priests that come together and say, you know what, this is what we're talking about and this is what we understand, and we don't really care if anybody else understands it or not. We don't really care if they have any knowledge to say anything against it or otherwise. We are the ones who are in control of the knowledge. So we have to think in terms of why we even talk about the theory of mathematics. What good is the theory of mathematics if the majority cannot understand it? Because I don't only believe, I'm totally convinced that everyone has an ability to do mathematics, not just the ones who are sycophants and who are able to follow teachers. Everyone has the ability if it's taught in the correct way. So pedagogy is one of the most important aspects of mathematics. And if you go back again to what Euclid did, he's one of the greatest teachers, so to speak, in my opinion, because what he wrote down was an attempt to answer everything that there was to know about what was being said or taught. That's why he was so meticulous in his approach. And that's why we need to be so meticulous in our approach. And proofs, contrary to Terence Tao's opinion, are very, very important, by the way. Proofs are important in mathematics, in not only mathematics, in every other field of science. Because if you can't prove something, you can't reproduce it, then what are you talking about, and what confidence can anybody else have that what you're saying is true? So you should be able to show or prove that what you're saying is true. Otherwise, it's meaningless.
Yes, and for me, Euclid was the first, let's say, pure mathematician in modern terms, because again, giving context to, if one studies the history of mathematics and ancient Greek mathematics, you will see that mathematicians prior to Euclid existed, but it was a collection of algorithms, intuition. Yes, there was the notion of proof, but what Euclid did, and Euclid was also a librarian, wasn't he, at the great library of Alexandria? So one can deduce from his work, what he did was accumulate all the mathematics and actually distill the essence in order to create a perfect program that begins with most fundamental, irreducible first principles, and then a methodology from which all mathematics can afterwards be derived. So, and it's also, you talked about the pedagogy of it. Isn't it perfect what the ancient Greeks did? They didn't learn mathematics, and you said about for the term mathematics in the etymology of the word, it has the Greek word to learn. It's sort of a meta-learning tool.
That's That's right.
And if you understand Euclid, you don't have to learn any more mathematics because you've learned how to learn. It's the absolute learning tool. So therefore, why waste time, resources, and memory in order to just parrot things, and instead of having the perfect mechanism from which everything can be derived?
Right.
And that's why their school system is so much more advanced than ours, because the only thing they did was a couple of subjects, which was, for instance, why should you learn things? If you learn how to read, then you can read and learn everything. And it's the same with mathematics. If you can reason, then you can reason about anything.
Correct.
So,
and once you learn to measure, you can apply that principle to every other science. That's why mathematics is so called the queen of sciences, isn't it?
yes, it's sort of a meta science. It's so you mentioned about genius, and I wanted to touch upon that. Sorry, yes, were you about to say something?
Yeah, the only difference between the science of mathematics and all the other sciences is that mathematics doesn't need physical experimentation or anything like that to show that it's true. All you need is reason. That's
Yes.
all you need with mathematics.
Yes, absolutely. So the cult of genius, you mentioned something, we mentioned Terence Tao, and everybody always references Einstein, although the theory's full of holes, and most people that reference Einstein haven't even read his works, by the way. But this whole cult of genius, would you like to talk about that in modern times? And
Yes.
we're constantly fed this by the media that he was a genius and you have to be a genius and his IQ is off the charts.
Well, first of all, did you know that Albert Einstein, never had an IQ test?
Exactly.
There's no record of Einstein ever having taken an IQ test.
It's crazy how people talk about IQ. IQ was invented, it's a test, and it was invented much later. So how can you talk about, can't people realize that? How weird is that, isn't?
It's very weird, and here it's not only very weird; it's laughable because the father of it, I think it was Alfred Binet, if I'm not mistaken, was a psychologist, and psychology, in my opinion, is a pseudoscience. It's not even a science. Okay, so although I have an extremely high IQ, it doesn't really define who I am. What defines who I am is my work. Okay,
Exactly.
you cannot sit down and take an IQ test, which I've done, by the way. You cannot sit down and take an IQ test and say, "Wow, because the results show that I'm a genius, I'm a genius." No, you're not. What it shows is that you have some sort of intellectual ability, but it doesn't mean you're a genius. Okay, so strictly speaking, an IQ above 160 doesn't make you a genius. Okay, and then the works of Einstein. Let's just go back to the works of Einstein. There's this constant thing about trying to prove that his theorem his theory is correct. But if it was correct in the first place, why are they trying to prove it all the time? Why are they reproving it? I mean, Einstein's theory is such absolute rot, and I'll explain to you one very simple reason why it is rot, because Einstein didn't have a clue what is the concept of time. And I put it to you that no theoretical physicist that I've ever known or met even understands what is the concept of time. He has no idea. He's got this vague notion that it's something that a clock tells you, or that it's so many cycles of cesium radiation per second or whatever. They don't have a correct notion of time. And if you look at the field equations, one of the core concepts is the time differential. And first of all, and then put together the fact that they don't really understand calculus, and what you get is this colossal mountain of confusion. It's all total garbage. And for lack of a better word, I just call it absolute rot.
Yes, and I mean, without too much mathematical background, I think one can one can understand, for instance, that this thing that was taken as a given, relativity and then general relativity, if you extend it, and so what does it produce? It produces a singularity, and then it produces the fact that, for instance, the universe is expanding something. It can be used in that theory. But isn't that illogical? Because how can the universe be expanding in comparison to what? And if it was expanding, then it wouldn't be the universe, because for something to expand, and taking this back to the basic definition of number, right?
That's
something
right.
has to be, for something to be, it has to be compared to something else, or it has to be measured to so how is everything expanding? If it would be expanding, it would be simply, it wouldn't be everything. So can't somebody simply, without any notion of complex mathematics, understand that, well, this is a logical flaw, therefore it cannot exist, so let's take it back?
And redo the theory. It's like going back to the analogy of 0.333. When is 0.333 equal to a third? After 10 trillion digits? After 100 trillion digits? When is pi equal to that little thing with 3.14159? When is it equal to that? After how many digits is it equal to that? It's never equal to that. Oh, so then it's not equal to that because it's not there, right?
Yes.
And then they might tell you the limit. But if you talk about the limit, then what are you talking about? Are you talking about a number or something that cannot be measured? Okay? The latter is what you're talking about. That's something that cannot be measured, because it's basically a constant that you're referring to when you attempt to measure. So infinity is one of the biggest problems in mainstream mathematics, in my opinion. And it has no place in mathematics or in any other field of rational thought. And of course, when some religious crank like the father of all mathematical cranks, Georg Cantor, comes along and says there are different levels of infinity and introduces things called the transfinite numbers, and says God revealed these things to him, by the way, over a period of 20 years. It's like, if somebody had to come to you today and say that to you, what would you do? What would your first reaction be? God revealed these things to me. Do you see what I'm saying?
Yes, of course. I mean, it was a lot of Cantor being established was sort of wishful thinking of mathematicians like Hilbert, that they wanted for the problem to be solved. And the funny thing is, the whole problem is that they never understood.
They never knew. They were clueless. From the beginning, they've been clueless. From the beginning. And they, I mean, I can't tell you how many books I've read where somebody says, oh, the ancient Greeks had a problem with this or with that. There's even a popular video on the internet by some PhD in Australia. It's on Numberphile, and it's called Euclid's Big...
I've seen it.
Yeah, Euclid's Big Problem. I think to myself,
terrible,
no,
disgraceful,
yeah.
disgraceful.
Yeah, no, Euclid knew what you were talking about. That's why he introduced the abstract unit in Book 7.
Yes.
Hello, yes, Euclid's saying that what you're saying is correct, and you knew about it. It wasn't a problem.
So, I want a brief discussion about Gödel's theorem, Platonism, and why I think that nobody has understood Platonism in millennia, maybe except you.
Well, that's a big subject. That's a big subject. Maybe we can do that in another video.
Yeah, well, this has already been quite long, so we can pause this and maybe continue on some other time.
Okay, and thanks for letting me chat with you and share these views.
Thank you very much.
Yeah, goodbye.
Okay, we'll talk. Bye.
Bye.